Hey there, my name is Gokul, and today I'm going to talk about our work on imitation learning in the presence of unobserved confounders. Consider the problem of trying to learn to fly a quadcopter by imitating an expert pilot. Let's assume there's heavy gusts of wind that cause the quadcopter to deviate from the intended straight path of the expert. Now, what will happen if we try to apply a standard imitation learning algorithm, like behavioral cloning, to this set of demonstrations? Well, the learner is likely to pick up on the correlation that being a little on the left is usually followed by going even more to the left. If they ignore the fact that it was the wind that was the root cause of this correlation, they might attempt to reproduce the swerving behavior of the expert, causing them to deviate even further at test time due to the continued influence of the wind. More abstractly, the effect of a confounder, like the wind in our previous example, is to introduce temporal correlations in the recorded actions that do not have their true cause in the recorded state. We can visualize this effect via a graphical model. At each time step, the expert takes an action responding to the observed state, and the MDP transitions to the next state. The persistent confounder U affects multiple actions. This means when we try to regress from states to actions, standard approaches will produce inconsistent estimates of the expert's policy. This is because the confounding travels through the dynamics to influence the next state, leading to spurious correlations between recorded states and actions. The learner might then latch onto these spurious correlations to explain away the effect of the confounder by misattributing it to some element of the state, leading to poor test time performance. This is what leads to the increased swerving in our quadcopter example. What we'd like is instead to learn a policy that flies as close as to straight as the expert does on a windy day. It turns out we can find such a policy by applying a technique from econometrics called instrumental variable regression. Consider trying to regress from x to y, both of which are influenced by a confounder u. Ideally, to mitigate the effect of a confounder, we would randomize over x via a controlled experiment. However, if we only have access to observational data, we can achieve the same effect via a source of randomness independent of the confounder. This variable is called an instrument, which we denote as z. The key idea of instrumental variable regression is that one can condition on the instrument z to counter the effects of the confounder. In our model, the past state acts as this instrument, as it is independent of future confounding. We can see this graphically by noting that s sub t minus 1 is independent from u sub t. An instrument technically needs to satisfy a few more conditions, and we detail them in our paper. We can leverage this past state instrument in two ways. The first is to train a policy via standard behavioral cloning. Then, via a simulator, use this biased policy's proposed actions on the past state to re-simulate the transition from the past state to the current state. This leads to fresh draws of s of t that no longer share a noise term with the observed expert action. We can then apply standard imitation learning to this new dataset to learn a causally consistent policy, a procedure we call double. We show in our paper how this is equivalent to solving a certain two-player zero-sum game between a policy player and an adversary that can upweight residuals based on the value of the past state instrument. We term it residual. Notably, this game theoretic procedure can be performed completely offline. Before we can talk about performance bounds, we need to talk a little bit about the different kinds of confounding. Let's think a bit about the problem of learning to drive via imitation of an expert driver. One kind of persistent confounder we might have to deal with is a faulty tire. Just like with our quadcopter example, the expert might be intending to drive perfectly straight, but the recorded actions might not reflect that. In some sense, our data is corrupted by the presence of this confounder. A different sort of confounder we might have to deal with is a traffic light that wasn't in the data that the learner trains on. Without knowing the traffic light is red, the learner might struggle to explain the expert's behavior. In both of these scenarios, the true cause of the observed action is not in the recorded data. The difference is in the relationship between the expert and the cause. In the bubble on the left, the faulty tire is a perturbation that is applied on top of the expert's intended action, so we term it exogenous noise. In the bubble on the right, the expert intended to respond to the traffic light, so we term it endogenous noise. At test time, a learner attempting to drive the car on the left would still be exposed to the exogenous noise of the faulty tire. However, a learner attempting to drive the car on the right would not have its actions affected by the endogenous noise, as they are still unable to observe the traffic light. While the difference between them is subtle, these two forms of confounding can lead to completely different performance characteristics for the learner's policy. We seek to answer the question of how well a learner can do in either of these settings. Let's start off by discussing the exogenous setting. We prove a performance bound for both of our algorithms in the exogenous setting, where epsilon and delta are measures of training error, kappa of pi, a measure of the weakness of the past state as an instrument, c, a measure of the smoothness of the noise distribution, and t, the horizon of the problem. Notably, behavioral cloning does not have a similar bound in the exogenous setting, so even if one drives BC training error to 0, they have no guarantee of recovering a policy of equivalent quality to that of the expert. In contrast, both of our approaches would be able to match expert performance if infinite sample training error was driven to 0. Empirically, we find that both of our algorithms are able to significantly outperform behavioral cloning at matching the intended action of the expert on a simulated lunar lander task with exogenous noise. We can also compare the output of one of our causally consistent approaches to behavioral cloning to find the areas of the state space where the effect of the confounder is particularly strong. For the lunar lander task, the more red dots indicate these areas, where behavioral cloning might be particularly biased. The story under endogenous noise is a bit more nuanced. Let's return to our traffic light example and consider two different reward functions that we could use to compare a learner and expert performance. The first is going to have 3 inputs: the state of the car, the steering action, and the state of the traffic light. The second is just going to get the state of the car and the steering angle as input. Under a reward function in the first form, it would be pretty easy to differentiate the learner from the expert. We could penalize the learner harshly for running a red light they don't know about, or for holding up traffic when the unobserved light is green. We prove a stronger version of this point in our paper, that there can be problems for which no Markovian policy is value equivalent to the expert. We note that this is equivalent to a result in a recent paper by Kamor et al. The takeaway is that in this setting, effective imitation can be impossible. Let's now consider the second reward function, which ignores the confounder. We note that such a functional form eliminates the natural reward function that penalizes the learner for not obeying the traffic light. We prove a surprising claim in our paper. For reward functions of this form, a perfect behavioral cloner will be value equivalent to the expert, while a causal imitation learning algorithm will not be. The intuition behind this result is that for a reward function of this form, one only needs to match the observed state action marginals of the expert, which is what behavioral cloning does. We can summarize our discussion over the past few minutes in a flowchart. Under exogenous noise, using one of our causally consistent approaches is recommended. Under endogenous noise and a restricted class of reward functions, behavioral cloning is the right answer. It is an open question to determine what the right approach is, if any exists, for endogenous noise with rewards that can depend on this noise. Let me now discuss a couple other details we touch upon in our paper. We also consider an extension to our previous graphical model where a confounder can affect more than 2 time steps. For example, the wind in our quadcopter example might affect quite a few time steps before dissipating. This sort of persistent confounder means one needs to reach back even further in time to find a valid instrument. States further back end up being weaker instruments as they are less correlated with the present. We plot the weakness of the instrument kappa for a linear quadratic Gaussian problem, and we see it grow exponentially with the persistence of the confounder. This tells us that the effect of the confounder sticks around for a long time will be significantly harder to remove. Kappa is a feature of the problem rather than of a particular algorithm. In some sense, it captures how ill-posed the question we are asking is. With that, I'd like to thank you for your time, and please check out our full paper, code, and videos at the link on the screen.